Yeah, let's start. Yeah, hi everyone. Yeah, welcome to the second workshop of the Free Deep Learning Week. Yeah, so I am Kim White and I'm currently a triple year 3 student in NTU. Yeah, so we are waiting them to join. Yeah, so before I start the session, yeah, so I would like to introduce about MLDA. Yeah, so okay, so MLDA Triple E is a student-centric lab which aims to provide a platform to empower our Triple E or IAM students learning and deploying of machine learning and data analytics skills and knowledge in both academia and industry. Yeah, we do so through our various events, projects, and activities. Yeah, and as a student committee of MLDA, our mission to execute and plan those events and workshops. And how we do it through help of our state-of-the-art faculty, resource and technical support to faculties. Your learning journey in machine learning and data analytics, which is the hot topic of the decade. We also impact knowledge and skills for machine learning through our 4 different pillars of events and activities, ranging from our machine learning projects, industry projects, and career events and workshops with completion. Yeah, so now MLD is having our flagship event, the Deep Learning Week, which is a 1-week long event that aims to promote machine learning via industry sharing and recruitment booth. So on the first day, which is next Monday, yeah, so there will be an industry night where we are doing a panel discussion with experts from the field of AI on the topic of how AI will transform the post-COVID world. And in the end, there will be a virtual career booth from many companies, whereby participants can network with the company and apply for jobs or internship. Yeah, so if you are interested, yeah, please register via this QR code. Yeah, this QR code is also available in MLDA Instagram or the NTU email. Yeah. Yeah. So wait for a while. Yeah. Yeah, sorry. Just now my chatbot is blocking the PPT. Okay. Yeah. So another part of the deep learning week is the workshop where we are conducting the workshop for all levels of expertise from the intro to Python and then to our transfer learning. Yeah, so please stay tuned for our social media, the Instagram, to get more info on each workshop. Yeah. Yeah, so before I start the session, yeah, so I will stop share for a while and I will take a screenshot of this Zoom meeting. Yeah. Okay, thank you. Yeah, before I start today's workshop, yeah, so let me to briefly talk about what today's workshop is. Yeah, so today's workshop we will have two sessions. Yeah, so the first session is the PowerPoint. Yeah, so we will talk about nonlinear classification, and then we will talk about the structure and of the multi-layer neural networks. Yeah, so in this PowerPoint, neural networks is described as NN. Yeah, and lastly, we will talk about the multi-layer model, and we will talk about some keywords, and we will talk about forward and backward propagation. Yeah, and the second part, yeah, and we will have a coding session. Yeah, so we will code a very simple neural network in a Google Colab. Yeah, okay, so okay. I think my screen is still blocked in the right side, right? Mm, yeah, let me share my, is that okay? Um, Okay, I fixed for a while. I hope it is better now. Yeah, so, okay, so firstly, we will talk about nonlinear classification. Yeah, and we can see, right, there are two figures here. Yeah, so the left figure, is data that can be separated by a straight line. Yeah, and then this we can solve this problem by using linear classification. Yeah, so, but if we have some data which is as a right side, yeah, and the only way to solve this problem is only have we have a like circular shape line that can separate this data from the others. Yeah. So if we are having like this type of data, so we can't solve the problem by just a linear classification. Yeah. So we introduce a non-linear classification here. Yeah. So linearly non-separable data cannot be efficiently be classified by using a single neuron. Yeah. So hence, we introduce a multi-layer neural network, which are non-linear classifiers. Yeah. So yeah. So basically, this is a very simple network structure. Yeah. So yeah. So what we can see is this simple structure consists of three layers. Yeah. So the first one is the input layer, and then the second one is the hidden layer, and then the last one is the output layer. Yeah, so basically the input layer and output layer consists of just one layer, and they can be a multiple hidden layer. Yeah, and and yeah, so assume that we are trying to classify a image here. Yeah, so firstly we will like make our image to be a linear. So we will expand our image by make it from a 2D image to a 1D image. Yeah, so we know that image basically will consist of pixel value, right? Yeah, so if we have a like 64 times 64 like pixel value, yeah, so we will make it in a 1D. So the 1D shape will consist of 64 times 64 pixel value also. Yeah, and then we will fatten up the uh, pixel value into a 1D shape. Yeah, so that will be our input. Yeah. So suppose that we only have one image, yeah, and our number of the input neuron will be will be 3 times the number of the pixel of a RGB image. Yeah, because we know that an image consists of RGB value, right? So it's red, green, and blue value. Yeah, so basically there are 3 channels, and each channel consists of, so if each channel consists of 64 times 64 pixel value, yeah, so we will have a input dimension with it, which is 3 times 64 times 64. Yeah, and then we will like try to make it to be a flatten it to be in a 1D shape. Yeah, so that will be our input value. Yeah, so okay, so I will also like want to introduce the weight. Yeah, so basically what is weight? Weight is the basically you can assume that weight is the connection. Basically you can like assume that weight is the connection between two layers. Yeah, so this W and then superscript 1. Yeah, so in this diagram is the weight connecting the input layer and the hidden layer. Yeah, so the weight superscript 2 will be the weight connecting the hidden layer and the output layer. Yeah, so this uh okay, we can see here the W, the J here basically means the weight connecting to the first neuron of the hidden layer. Yeah, so if we have like 2 neurons here, yeah, so the J will be 1, 2, or 0, 1. Yeah, assume see whether like which programming language you are using. Yeah, so the K here will also denotes by the weight connecting to the K neuron of the output layer. Yeah, so we can see that W will be a like collection of the weight connected to different neuron from W1 to WD. Assume that there are D neuron here. Yeah, so W1 basically is all the weight that connected to the first neuron. Yeah, and that's applied all of the for all the neuron until D. Yeah, so the dimension of W will be n times D. Yeah, so n is the number of the input layer. Yeah, so W superscript 2 is the collection of all the neuron connected to the output layer. Yeah, so if our output layer consists of like multiple neuron, yeah, so we have like W1, W2 to WC. Yeah, so our W superscript 2 will have a size of D times C. Yeah, so W1 and W2 are the weight in the first layer and second layer. Yeah, so let's continue. Yeah, so we also have A. Yeah, so the A is the output of the first layer. Yeah, so assume that we have like D neurons here. Yeah, so A will be the output of all the neurons, like A1 to AD. Yeah, and Y is the output of the second layer, which is the output layer in this simple model. Yeah, so if they are like C output neurons, yeah, so Y will be Y1 to YC. Yeah, so what is the so like we know that the input of the neuron is basically the pixel value from the image, right? Yeah, so what is the input of the first hidden layer? Yeah, so basically it's just the input. Yeah, because the input you can assume it as a floating number. Yeah, so the pixel value, yeah, so basically is the input multiplied by its weight. Yeah, and then also the second input multiplied by its weight connecting to this neuron to this neuron. Yeah, so and then we will talk about this in the next slides. Yeah, yeah, so A, just now we can see the A is the output of the first hidden layer. Yeah, so the A will be a function of W transpose and X. Okay, so I will explain this in the previous slide also. Yeah. So what is F? F is the activation function. Yeah, I will explain this function later on. Yeah. So we can see right just now we can see the A is the activation function of the W transpose multiplied by the X. Yeah. So because we know that W, yeah, so we just because we are just looking at the first neuron, right? Yeah, so we can just look at the W1. Yeah, so basically W1. Yeah, so W1 have the dimension of n times 1. Yeah, and the input also have the uh, dimension of n times 1. Yeah, so we will take the transpose of W. Yeah, and then the transpose basically we will like swap the column and the row of the array. Yeah, so after that, this W transpose will become a dimension of 1 times n. Yeah, and then X have a dimension of n times 1. Yeah, so by the properties of matrix multiplication, yeah, so the output will be a 1 times 1 array. Yeah, so basically just a floating number. Yeah, so and then that is the input to the first hidden layer. Yeah, and then that's applied the same to the output layer also. Yeah. So y is also, so y is the function of the W2. W2 is the weight connecting the hidden layer and the output layer. And A is the output of the first hidden layer. Yeah. So by substituting the A inside, yeah, and then we can get this equation. Yeah. So what is activation function? Yeah, so if our activation function is a linear function, yeah, so basically, yeah, so basically Fi is equal to R. Yeah, so we can assume that the F can be removed. Yeah, so if Y is equal to this equation from here, yeah, and then the F can be removed, and then we can get basically just this value. Okay, and yeah, so by the properties of matrix multiplication, W2 transpose, W1 transpose is basically W1, the transpose of W1 and multiplied by W2. Yeah, and then if we combine this W1, W2 together, and then we can get the U transpose. Yeah, U is equal to W1, W2. Yeah, so if our activation function is just a linear function, Fi is equal to R, then we will get the output. It will be the same as the single layer network. Yeah. So that's why we are introducing a non-linear activation function. Yeah, and then we will see what are the example of this activation function later. Yeah. Yeah. So to design a multi-layer neural network, it's very important to have a non-linear activation function. Yeah, at least for the hidden neuron. And then we will be looking at there are some very famous activation function that they will be using in the deep neural network. Yeah. Yeah. So the first one I will like introduce the ReLU function. Yeah. So ReLU means for rectified linear unit. Yeah. So basically ReLU is the graph of ReLU in the XY plane is basically like this. Yeah. So if the input the V is less than 0. Yeah. So yeah, so if the input is less than 0, yeah, so the output will be 0. Yeah, so if the input is larger than 0, so the output will be same as the input will be V also. Yeah, and we can also denote the ReLU function by the maximum of the input and 0. Yeah, so if the input is less than 0, the output will be 0. So if the input is larger than 0, yeah, so the output will same as the input. And then we will talk about sigmoid function. Yeah. So the graph of sigmoid function in the xy plane is basically like this. Yeah. So the formula of sigmoid function is basically can be derived at 1 over 1 plus exponential of minus v. Yeah, v is the input. Yeah, so um, basically we are using the ReLU function in our hidden layer and the sigmoid function in our output layer. Yeah, because sometimes we are dealing with regression problem. Yeah, and then we want our output to be in the range of 0 to 1. Yeah, so by using this sigmoid function in our output layer, yeah, so we can like fix our output to input to be in the range of 0 to 1. Yeah. Yeah, and now we are going to talk about the concept of the multi-layer model. Yeah. Now we are introducing like two keywords, yeah, called forward propagation and also the backward propagation. Yeah. So uh, what prog so forward propagation we have to is mainly to basically is just the input and then multiply by the weight, and then it go through some activation function, and then we get the output from the hidden layer. Yeah, and then the output of the first layer of the hidden layer will also go into the second. This is the output layer, and then it will also go through some like activation function, and then it will have the output. Yeah, so the purpose of the forward propagation is to obtain the output. Yeah, so and the purpose of the backward propagation is to obtain the error, and then we will update the weight. Yeah, so basically the arrow here is the forward propagation direction, and then the dotted line is the backward propagation direction. Yeah, and then we will talk about this later on. Yeah. So as just now we said, right, the input and then like multiply by like these weights, and then go through some activation function, and then we will get the output of the first layer, and then we will like go through the maybe the output layer and then the activation function, and then we will get the output. Yeah. So since we are like doing supervised learning, yeah, so we will have the real label or the actual label of the output. Yeah, so we can like calculate the loss from this. Yeah. Yeah, so why we are using the backward propagation? Yeah, so backward propagation is to update the weights W1 and W2. Yeah, so if you are like have some experience in neural network, maybe you will see a term called bias. Yeah, but uh, in this PowerPoint, and then we will like already include bias inside the weight. Yeah, you can see bias as the neuron with the weight of 1. Yeah, so bias basically is you can see bias as the constant in a in a function. Yeah, so yeah, so since we are doing a supervised learning, yeah, so that we know that the the actual output or the actual target at the last layer. Yeah, and then we can calculate the loss by some loss function. We will also like introducing loss function later. Yeah, but the target is not available in the hidden layer. Yeah, so we know that the difference between the actual value and the output after the value on the output layer, right? Yeah, but we don't know what is the target is inside the hidden layer. Yeah. Yeah, but the activation function is smooth and continuous. Yeah, just now I show like two examples, right? The ReLU and the sigmoid function. Yeah, both are smooth and continuous. That means they are derivable. Yeah. So that, yeah. So how do we like update the weight? Yeah. So initially we will randomly assign the weight in the model. Yeah. So we can do it by like loading the weight, or we can randomly assign them. Yeah. So, and how to update the weight? Yeah. So from the previous slide, right? Yeah. So we can know that the output basically is the output of this layer multiplied by the weight, right? Yeah. So the output of this layer will be a function of this weight also. Yeah. And then the output of the layer will depend by the input of this layer, right? And then the input of this layer will also be the input layer multiplied by some weights, and then we will get the input for the hidden layer. Yeah, so the input of the hidden layer will also be a function of the weight, right? Yeah, and then by using chain rule, yeah, and then we can like uh because like the output will also will be a function of this weight, and then will also be a function of this weight also. Yeah, and then we will derive, and then so that we can derive the derivative by using the partial derivative of the loss by different in respect to different weights. Yeah. So basically, update the weight is by using the weight is equal to weight subtract the step size. Yeah. So this is the step size or learning rate multiplied by the derivative of the loss function with respect to the weight. Yeah. And then this also applicable to the weight superscript 2. Yeah, so what is J? Yeah, J basically is the loss function. Yeah, and then the loss function is a function of the W superscript 1 and W superscript 2. Yeah, so it basically is the error, E is the error, yeah. Error square, and then the E here we will define is the absolute difference between the T is the actual target, and then Y is the output. Yeah, and then we will get the square. Yeah, so there are also like different loss function. Yeah, so now we are doing a simple one. Yeah, we are taking the absolute difference between the actual target and the output of the model, and then we take the square. Yeah, so what is the step size, right? Yeah, so we assume that the x-axis is the weight, and then the y-axis is the loss. Yeah, so our purpose is we want the loss to be as low as possible. Yeah, so this point will be our target. Yeah, so assume that initially we are at this point, right? Yeah, so the derivative of this point will be a positive value, right? Yeah, so if we are if we are subtracting the derivative, and then we will like go closer, maybe we will like go to this value. Yeah, and then the derivative of this point will also be a positive value, right? Yeah, so if we are subtracting the positive value, maybe we will like go inside a bit. Yeah, maybe we will go to this point, and then the derivative of this point will be a negative value, and then we will subtracting this negative value, and then we will get a positive number, and then we will increase a bit. Yeah, so maybe we will reach this point. Yeah, so why we are introducing the step size is because we want it to like to decay like not so fast, because like if we are not using our step size, yeah, so sometimes if our gradient is too large, maybe we will like just jump between these two regions, but we will not reach the uh, lowest point. Yeah, but if we like defining our step size to be too small, yeah, so maybe we will every time uh we update our weight, we will just like increase slowly. Yeah, so we will take a very slow time to converge. Yeah, so it's like very important to take a appropriate step size or learning rate. Yeah, so just now the way I say to update the weight by like we minus the gradient in this point is basically called gradient descent, and this is a very simple like optimizer. What you call optimizer is the way we update the weight. And then there are also like a lot of popular optimizer which is far more complex than this one. Yeah. Yeah. We are like introducing the backward propagation learning formula. Yeah. So this formula consists of like some basic mathematics in the matrix multiplication, yeah, and the matrix calculus, yeah. So if you are not familiar with the formula, yeah, it's totally fine. Yeah. So I am not going to derive the equation now. Yeah, but the formula to derive the equation will be at the last slide of this PowerPoint, and this PowerPoint will be show to you later. Yeah. So if you are like have any like question regarding to how to derive this equation, you can see the appendix of this PowerPoint, which is the last page. Yeah. So basically, W is equal to W subtract the step size and the derivative respect to their weight. Yeah. So since we are using the like one input layer, one hidden layer, and one output layer model, right? Yeah. So the final output is in this form. Yeah. And then the weight one is the weight superscript one, and then we minus the partial derivative of the loss function uh in respect to the weight. Yeah. This will so the final formula for this is this one. Yeah. So the derivative of this will be in the last page of this PowerPoint. Yeah. So yeah, we are also like introducing the sigmoid function and its derivative. Yeah, so sigmoid function basically is 1 over the 1 plus exponential of minus q. Q is the input. And then the range of the input is in the from 0 to 1. Yeah, and then the f prime q, the derivative in respect to q is the exponential of minus q over the square of 1 plus exponential of minus q. Yeah, so like if you arrange this formula, you will get fq over 1 minus fq. Yeah, so please remember this formula. Yeah, so we can see like if we are having this formula, right? So if we want to calculate the derivative, the input will be also very important. Yeah. Yeah, so now we are going to talk about the training procedure of the neural network. Yeah. So initially we will initialize. So maybe we'll initialize how our model to be like how many layer or like how many neuron in each layer. Yeah. So and then we will also like pre-process our training sample. Yeah. So as the example just now, we will flatten the 2D image into a 1D array. Yeah. And then we will feed the input into the model, and then by going through some like addition and multiplication of weights, and then and also going through some activation function, we will obtain the loss. We'll obtain the output. Yeah. So in the progress of the forward propagation, the weight is no change. Yeah, the weight is still there. Yeah. So after obtain the output, and then we will compare the output with the actual target or actual label. Yeah. So by using the loss function, we can compute the loss at the output layer. Yeah. And then by using the loss, we will perform the backward propagation. Yeah. So the backward propagation is to update the weight so that we can get a more, we can reduce our loss, or we can make our accuracy to be higher. Yeah. So, okay, after we update the weight, then we will see whether our stopping criterion is met. Yeah. So what is our stopping criterion? Yeah. So maybe you will set the model to loop over the input for maybe 100 apple. Yeah. You will loop through the input for 100 times, or we set the criterion maybe if the accuracy reach like 99%. Yeah. So we will stop this looping. Yeah. And then we will get out of the model. Yeah. So if we are not meet the stopping criteria, so what we do, we will go over the input again. Yeah, so we will feed again the input. Yeah, so basically maybe it's the image. Yeah, so we will fatten the image again, and then we will input to the forward propagation. Yeah, and then we will get the output, get the loss, and then we will get the gradient. We will compute the backward propagation. Yeah, so and we will update the weight, and then we see if do we like obtain the stopping criterion. Yeah, so if we obtain, and then we will end our training process. Yeah. So yeah, so basically this is the PowerPoint presentation. Yeah, and then now we will have a 10 minutes break. Yeah, so in this break I will share a Google Drive here. Yeah, so please enter this Google Drive and add the Google Drive into your own drive. Yeah, so I will stop share for a while. Yeah, and I will paste the link here. Yeah. Can you guys like enter the link? Yeah, so if you enter the link, right, I will share my screen. Yeah, so if you enter the link, right, you will reach a Google Drive. Yeah. So please click this button, and then you add a shortcut to your drive. Yeah. So like after you add your shortcut to your drive, so that we can proceed to our next step. Yeah. Yeah. So like there are like a few folder and a few files here. Yeah. So this PowerPoint basically is the PowerPoint just now. Yeah. And then this DNN app utils version 3.py basically is the Python file, consists of the helper function that you will be using later. Yeah, and then this one will be the IPython notebook that we will be using for our coding session later. Yeah. And then the data set basically is the data set that we will use, and then the images is we using to test our performance of the model. Yeah. So if you are done like adding the shortcut to your drive, right? Yeah. So please like double click this, the neural network.ipimb. Yeah. And then please open the file by using the Google Colab. Yeah. So if you don't have the connected apps here, right, you can you can connect more, you can press the connect more apps here, and then try to find the Google Colab. Yeah. Yeah. So we wait for a while. Yeah. So after that, if you are able to find your your connected apps there, and then you will be directed to this page. Yeah. So this is the place where we will have our coding session later on. Yeah. So let's have a 10 minutes break, and then for you to like maybe you add to your drive, or like you open this IPython notebook. Yeah, and then we will start our second session. Yeah, in 10 minutes. Yeah. So if you have any question, you can ask in the chat box. Yeah. So we have a helper that will um, help you to maybe to solve the problem. Yeah. Is anyone have problem with like opening the Google Drive, or like, yeah? So please log into your Google account. Yeah, or else you cannot like open this Google Drive. Yeah, because later we will have to like um go into your Google Drive, yeah, to access some file. Yeah. So if you are like not logged into your Google Drive, yeah, so maybe you can't like access it. Oh, hi. Yeah. So, can you like go into the chat in the link? Yeah. So just now, for those who just joined, yeah. So I've like posted the link of the Google Drive inside the chat. Yeah. So please like click into the link. Yeah, and then you like proceed to this page. Yeah. So please click on the like add shortcut to Drive. Yeah. So that we can like proceed to the next step. Yeah. So like after you add this one. Yeah. So you can like open this by clicking the neural network.ipynb. Yeah, and then no preview is available. Yeah, but you can open the notebook by using the Google Colab. Yeah. Yeah. So like after you open it, you will be directed to this page. Yeah. So we will begin in 2 minutes. Yeah. Yeah. So let's proceed to our second session. Yeah, the coding session. Okay. Yeah. So let me talk about this code first. Yeah. So this code basically we're doing a simple classifier. Yeah. So we want to classify is the image is the cat image or not the cat image. Yeah. So just two categories. Yeah. Two classes is a cat or not a cat. Yeah. So the output basically is 0 or 1. Yeah. So okay. So this code basically the purpose is to classify a image. Yeah. So for those who are new to Google Colab, yeah, or new to the Jupyter Notebook, yeah. So the so in Google Colab we can run our cell one by one, yeah, but we are not running all together, yeah. So if you separate your code into different cell, right, yeah. So you like you can run it by one, yeah. So the way to run a cell is either by pressing this run button or you press Shift Enter, yeah. So then it will run. Yeah. Also, please make sure that this one is connected. Yeah. Now it is connecting because I offline for time. Yeah. So after it is connected, right? Yeah, the RAM and this will come out. Yeah. So okay. So the purpose of this code is to connect our Google Colab to our Google Drive, so that we can access our like material inside the Google Drive. Yeah. So now we need to enter your authorization code. Yeah. So just go into this link. Yeah. And then you go to this page. Yeah. Yeah. So like please like sign into the account. Just now you add your the workshop drive inside. Yeah, just now you add your this drive, right? Yeah, so you have to sign into the account same as that drive. Yeah. Okay, then you just allow it. Okay, then you will see a code. Yeah, so area code is different. Yeah, so like you can't copy my code. Okay. Yeah, so please copy your code and then you will paste it here. Yeah, just paste it and then enter. Yeah, so if you are success, yeah, so it will be mounted at your content drive. Yeah, so okay. So like after that, you press the file button. Yeah, so you can see the drive is already added to your collab. Yeah. So we will copy this path. Yeah, and then will be copy the path here, copy path, and then we will place in the CD. Yeah, so if maybe you add in the different, maybe you add in like other file, right? Yeah, so you have to find the directory of the path of the file of the like neural network workshop, and then you cd here. Cd basically that you want the directory to be in this file. Yeah, and you can shift enter. Yeah, so if you success, then this output will come out. Yeah. Yeah, so okay, after that we are done with our we are done to mount our Google Lab onto our Google Drive. Yeah, okay, then we will import our libraries that we will be using here. Yeah, so basically some popular library is NumPy. Yeah, a library that can is like very good to do some matrix or array operation. Yeah, and then Matplotlib. Yeah, a library to like plot graph. Yeah, to like visualize your data or your output. Yeah, and then the PI is the function that can like dealing with load images, opening images. Yeah, and this DNN app utils is the Python file I show you uh inside the like Google Drive just now. Yeah, so this consists of the function that I'll be using later. Yeah. So and then here and then we load we run this cell and then we're done with our setting. Yeah. Okay. Yeah. So yeah. So yeah. So then we will load our data set. Yeah. So this function train x original, train y, train x, test x original, and test y, and classes will equal to load data. Yeah. So what is load data is a function inside the Python file just now. Okay. Yeah. So um, getting invalid syntax when I'm trying to load into the neural network workshop. Yeah. So our helper will try to help you. Yeah. So yeah, basically the load data will split our data set into train train set. Yeah, so this train x original will consist of the images. Yeah, and then the train y will be the actual label of the train set. Yeah, and then we also like want a small portion of the images to be our test set. Yeah, and then this test file will be the actual label of the test set. Yeah, and then the classes basically is just a cat or non-cat. Yeah. So like if you are interested in the what is actual the function load data is, yeah, you can check the Python file over the Python file just now. Yeah. And then we will, yeah, so like don't forget to load this cell. Yeah. So like if we are like success to load a cell, right? Yeah, so the number will assist here. Yeah. So now we want to like we'll try to see one of the image. Yeah. So now we are looking at the 10 example inside our train set. Yeah. So the train X original index will be the index is 10, right? So this will be the 10 uh train set. Yeah. And then we will try to print out the image and also the label of the image. Yeah. Yeah, so this is the non-cat picture. Yeah, so this is the actual, this is the like actual label of the image. Yeah, so later we will want our model to be like as close to this value. Yeah. Yeah, then we will explore our data set. Yeah. So we run this file. Yeah, so basically what this file is doing is we will tell you what is the size for our train set and test set. Yeah, so number of train example is 209. Yeah, so basically we will have 209 images inside our train set. Yeah, and then the number of tested example is 50. Yeah, so we will have a 50 example inside our test set. Yeah, so why do we need to like split the data set into train and test? Because when we are training the model, right? Yeah, the input of the model is just the images from the train set. Yeah, so for the whole training progress, right, the model won't see the test set. Yeah, so the test set is to like we want to uh if after we end our training process, right, we want to like test where is it the model can perform well. Yeah, so we are using our test set to test it. Yeah. So if we are using the same data for the training and test, right? Yeah, maybe the model will somehow will be like memorize the image and the label. Yeah, so maybe the accuracy will be very high. Yeah, so we are introducing a test set which the model won't see for the whole training progress. Yeah, and yeah, so each image is of size 64 times 64 times 3. Yeah, so 64 and 64 is the height and width of the image. Yeah, so basically the image will be a 64 width and 64 height. Yeah, and then 3 is the number of channel. Yeah, so why is 3? Because the image is the like color image, which is what we call it RGB image, right? Yeah, so consists of the R channel, G channel and B channel, the red, green, blue channels. Yeah, so we have 3 channels. Yeah, so for each channels we have 64 times 64 pixel value. Yeah, so this make up for the whole image. Yeah, so train X original shape will be 209 times 64 times 64 times 3. Yeah, so basically this consists of 209 images of 64 height, 64 width, and 3 channels. Yeah, so the train Y shape is 1 and 209. Basically, this is the label of each image. Yeah. And then the train X original shape will be a 50 times 64 times 64 times 3. Yeah, so basically we have 50 image of the shape of 64 times 64 times 3. Yeah. So the test Y shape will be a 1 1 and 1 times 50. Yeah, so basically this is the label of the test set. Yeah. So is there like any question for this part? Yeah, got someone asked like where to get the path. Yeah. So yeah, so if you have question, you can just type like for everyone, yeah, so that our helper can help you. Yeah, so you mean this path, right? Yeah, you can after you mount your Google Drive, you can like go to this folder, yeah, and then you can go to copy the path here, copy path here. Yeah, then you can paste it here after the CD space, and then you paste it here. Yeah, so that you can the directory will be inside the inside your folder. Yeah. Okay, so if you are okay with this cell, and then we will proceed to the next cell. Yeah, so now we are going to reshape the training and test example. Yeah. So, okay. Yeah. So train X flatten is equal to train X original shape. Yeah. So I move up a bit. Yeah. So this shape is equal to this one, right? Yeah. So train X, right? Yeah. And then we will reshape it. Yeah. So we will reshape it by train X original dot shape 0 is basically the index 0 inside the this shape. Yeah, so maybe a 209. Yeah, and -1. Yeah, so what -1 do? Yeah, so now we have our train set, yeah, of the shape of 200 and 209 2D image, right? Yeah, so now we have to flatten the whole image into a 1D array. Yeah, or like 1D vector. Yeah. So yeah, so this dot reshape is to reshape in this size, right? Yeah, so we want it to reshape in the 209 times a 1D vector. Yeah, but we don't know what is the shape of what is the length of the 1D array or 1D vector. Yeah, so we can use the -1 here. Yeah, so this basically the function will like automatically help us to calculate what is the shape after this reshape. Yeah, so you can also like replace the -1 by 64 times 64 times 3. Yeah, basically you get a like 5-digit number. Yeah, yeah, but you can use -1. Yeah, so to like simplify the progress. Yeah, so and then we will dot t is transpose. Yeah, and then we have to transpose the image. Yeah, so basically we will swap the column and the row of the train X flatten. Yeah, and then this also apply to the test X flatten. Yeah, and then okay, now we have 209 1D image. Sorry, 1D array. Yeah, so now we will try to flatten it. Yeah, so after we flatten it, we will like divide it by 255, right? Yeah, so why we want to divide is because we know that the pixel value is from 0 to 255, right? Yeah, so because we want our input to be between 0 and 1. Yeah, so we will like divide all the, we'll do the element wise division. Yeah, we will divide each pixel value by 255. Yeah, and then so that our input will be in the range of from 0 to 1. Yeah, and then this also like apply to the test X. Yeah, then we try to print the shape of the train X and test X. We run the cell. Yeah, sorry. Yeah, so we can see that the train X shape if is in a 200 209. Yeah, so why we will get this shape, right, is because 64 times 64 times 3 is basically the 12288. Yeah, so you can try to use the calculator to calculate this, right? Yeah, so basically this Yeah, so this line will help us to reshape our chain X original, yeah, from 209 times 64 times 3 into 209 times 12288. Yeah, so after we transpose it, yeah, and then we will get a 12288 times 209. Yeah, so in this, like in this code will reshape our 10x original into 209 times 12288. Yeah, so after we get the transpose, yeah, so we will swap the basically swap the two value here. Yeah, so we will get the 12288 times 209. Yeah, and this also apply to the test shape. Yeah, and I hope this because this divide, this flatten and divide is quite important. Yeah, so I hope this is clear for you. Yeah, yeah. So yeah, I think got a question. Yeah, can you explain why we need to divide by 255, right? Yeah, so because we want our, because the pixel value, yeah, so the image, right, if you like look in the, maybe you look, you transfer it into a image, into a like pixel value, right? Yeah, you can see the image basically is just a bunch of pixel value. Yeah, so the pixel value of a computer by default is from 0 to 255. Yeah, so but we want our, like, we want our input to be from 0 to 1. Yeah, because we don't want to have a, like so much range, right? Yeah, so basically we will divide the every pixel value by 255. Yeah, so that we can like have our input to be from 0 to 1. Yeah, yeah. So yeah, I think like after mounting, if you cannot find the path, maybe you don't add the, maybe you don't add the, like, because you have to sorry, answer to some question first. Yeah, so here you have to add this to your shortcut to drive, so that you can the path will be appear in your own drive. Yeah, okay, so let's continue. Yeah, okay, so these are just comment but not code. Yeah, so now we will define our two-layer neural network. Okay, yeah, so now we will have some helper function. Yeah, so this function is in the like Python file in the Google Drive. Yeah, so if you are like have interested in what is inside this function, yeah, you can try to like download the Python file and then you open it yourself. Yeah, and then you can see it. Yeah, so yeah, so basically there are like 5 or 6 uh helper function here. Yeah, so basically the function you may need and their inputs are, yeah, so these are the function. Yeah, so okay, so I will explain the function one by one. Yeah, so I think there are some question in the chat. Yeah, does that mean each pixel in the image has a value between 0 to 255? Yeah, yeah, yeah. So okay, so def is the, like, we can define a function by using this. Yeah, so initialize parameter. Yeah, so it will require 3 input, the nx, nh, and ny. Yeah, so what the function initialize parameter do is, after we define our like neural network, yeah, how many layer we want, and then how many like neuron in each layer, yeah, and then we want to like initialize the weight there. Yeah, because we don't want the weight to be like all is 0 or like all is 1 in the beginning. Yeah, so we are trying to like initialize the weight with some random value. Yeah, so this function will try to like initialize the all the weight inside your model, and then it will return you the parameters. Yeah, so parameters basically is a dictionary that contain your parameter. Yeah, so okay, now we are trying to do a two-layer model. Yeah, so we will building a two-layer model by input layer, and then is connected to the hidden layer, and then is connected to the output layer. Yeah, so the activation function inside the hidden layer is ReLU function, and the activation function of the output layer is the sigmoid function. Yeah, because you want the output to be in the range of 0 to 1 also. Yeah, so the output activation function, we are using sigmoid function. So just now as shown in the PowerPoint, right? Yeah, so the like the two-layer model have one input layer, one hidden layer, and one output layer, right? Have two weight, right? Yeah. So the weight W1 is all the weight that connected to the between the input layer and the hidden layer. Yeah. So W2 is the weight that connected all the hidden layer to the output layer. Yeah. So and here we have also B1 and B2. Yeah. So B1 is basically the bias inside the bias inside the input layer. Yeah. And B2 is the bias in the hidden layer. Yeah. So this bias is, you can see it as the constant inside a polynomial function. Yeah. So this function will return a parameters. Yeah. So this is a dictionary, consists of W1, B1, W2, B2. Yeah. So this shape is already included in the PowerPoint just now. Yeah. So you can if you are not understand, you can refer to the PowerPoint. Yeah. Yeah. And what is NX? NX is basically the number of neuron inside the input layer. NH is the number of neuron in the hidden layer, and NY is the number of neuron in the output layer. Yeah, so the weight connecting the input layer and the hidden layer is of shape of NH and NX. Yeah. So let's go now. Yeah. And then linear activation, there are a function called linear activation forward. Yeah. So this will take a input A previous is the activation from the previous layer or input data. Yeah, so if you are in the hidden layer, right? Yeah, so your input will be the input. Yeah, so it's basically the input basically is the image array. Yeah, and then W is the weight. Yeah, and then B is the bias, and then the activation. Sorry, um, I close this first. Yeah, yeah. So the activation will basically is the activation to be used in this layer. Yeah, it's stored as a text string. Yeah, so you can define it by using sigmoid or ReLU. Yeah, so it will return A. A is the output of the like output after that layer or output after that activation function. Yeah, and a cache. Yeah, so what is a cache? Cache is a dictionary that containing all your previous input and your previous weight. Yeah, because when calculating the derivative, right? Yeah, so we will have sometimes we will have to use the previous calculated weight and also the previous output. Yeah, so we don't want it to be disappear. Yeah, so we store all of it inside the cache. Yeah, it basically is a dictionary. Yeah, so we are also having a function called compute cost. Yeah, so um this compute cost will accept input AL. Yeah, so AL will basically is the output of your neural network or the output of your model. Yeah, and Y, what is Y? Y is the actual label of your the actual label of the image of the input image. Yeah, so your input image is the array, right? Is the like 1D shape array, right? Yeah. So the array will like going through like multiple addition and multiplication, and then go through some activation function, and then we will get the output AL, and then we will like compute the cost of the, mainly is compute the difference between the AL and the output and the actual labor. Yeah, so that we can return a cost. Yeah. So so the loss function we are using is cost entropy. Yeah. So if you are like interested what is the cost entropy, yeah, you can try to like Google it or try to like see inside the Python file just now. Yeah, the function is already defined there. Yeah. So after we obtain our loss, yeah, or the cost, yeah, loss and cost are the same thing. Yeah. So like, after we obtain our cost, yeah, then we will try to like go to proceed to the backward propagation. Yeah. So this linear activation backward will try to like update the weight. Yeah. So it will we will have the input dA is the post activation gradient for current layer, and then basically is the gradient of the like partial derivative of the loss compared in respective to the weight. Yeah. So dA, yeah, and the cache. Yeah. So just now we already like store our thing inside a cache, right? Yeah. So if we want to like because we want to, in calculating the like subsequent gradient, right, we have to use the value inside our cache. Yeah. So we pass the cache also, and then the activation function. Yeah. Just now, like in the PowerPoint, we have already said that like we have to like calculated the activation, the derivative of the activation function. Yeah. So we have also like tell the function that what is this layer do? Yeah. What is the activation function of this layer? And then it will return the dA previous. Yeah. So it's basically it will return the gradient of the next layer. Is because like now we are like propagating from the back to the front, right? Yeah. So we will like return it a value which is the layer which is like more in front. Yeah, because we are propagating from the back to the front, right? Yeah. So this one is the layer which is more backward. Yeah. So it will return like the output which is like more in front. Yeah. So dw is the gradient of the cost with respect to w, and then the dB, which is the partial derivative of the loss with respect to the w. And then dB we also like is the gradient of the cost with respect to b. Yeah, with the bias. Okay, then we will have a function called update parameters. Yeah, so after the backward, right, we have already like obtained the dw and dB. Yeah, so after that we will have to like update the function by just now we say we will like update the function by using gradient descent. Yeah, so this function basically is update the parameters by using the gradient descent. Yeah, so the input will be a parameters. Yeah, so it's basically a Python dictionary like containing your parameters. Yeah, so just now, yeah, parameters is also the like output of the first function just now we say about. Yeah, so and the grades. Yeah, so the grades is basically the a dictionary consists of, just now you calculated the dw and db, right? Yeah, so grades is basically is the dictionary of that, and the learning rate. Yeah, so the learning rate just now we talked about is the how much do you want to update the weight. Yeah, it will also return a new parameters. Yeah, so is the dictionary containing your updated parameters. Yeah, so this will be a maybe like parameters of w plus your string. Yeah, so because it is updated, right? Yeah, so Okay, then, okay, so there are some constants defining the two-layer model. Yeah, so, and next is the input of the, is basically the input in the first layer, right? The input layer, right? So our image have 64 times 64 times 3, right? Yeah, so we will fatten it into a 1D array or like 1D vector, right? Yeah, so NX will be a 64 times 64 times 3. Yeah. And then we have 7 neuron inside the hidden layer, and then we have 1 neuron in the output layer. Yeah, so the output of the 1 neuron, the output of the NY is basically tell us how much is the probability of the image belong to which class. Yeah. So the layer dimension is 12288, 7, and 1. Yeah, so we have 12288 for the input layer, 7 neuron for the hidden layer, and 1 neuron for the output layer. Yeah, so yeah, so in, yeah, how do we determine the number of layer for the hidden and output layer? Yeah, so this question is like basically if you are like new to this, yeah, you can try you can try yourself. Yeah, so basically as long as the weight is the dimension of the weight is same as the dimension of your layer, the neuron of your layer, right? Yeah, basically the whole function can run. Yeah, so the model can like propagate forward and backward. Yeah, so if you want maybe want some model that are like high accuracy, yeah, so maybe you have to like find online. Yeah, you can see like how they define their layer. Yeah, so now we will define our two-layer model. Yeah, so depth two-layer model. Yeah, this function will form a two-layer model. Yeah, so the input X is the basically is just now the 1D array. Yeah, so input image and then we fit into array, right? Yeah, so it's X. So the Y is basically the actual label of that 1D array. Yeah, so basically is a 0 or 1. Yeah, so basically 1 is a cat. Yeah, and 0 is not a cat. Yeah, so layer dimension is the, just now we say is the 12288. Yeah, this is the layer dimension, right? Learning rate is equal to 0.0075. Yeah, so the learning rate we set it as yeah. So if you want to ask like how do we determine the learning rate, yeah, you can. It's also like you have to explore yourself so that it won't like it can like converge to a lower loss. Yeah, and then the number of iteration is 3000. Yeah, so we want it to like go through like go through the input 3000 times. Yeah, and then yeah, so the argument is here. Yeah, so uh number of iteration is the number of iteration the optimization loop. Yeah, so it will loop through the input 3000 times, and then the print cost. Yeah, so if set to true, it will print the cost every 100 iteration. Yeah, so it will return a parameters that contain your weight and biases. Yeah, so okay, np.random.set is basically you define a seed so that you can perform a random initialization later. Yeah, so rest is you define a like empty dictionary first. Yeah, so and you define a empty list for your course. Yeah, and then the m is x dot shape 1. Yeah, so basically this is the number of examples. Yeah, so yeah, so our x dot shape, so our x now is 12288. Yeah, so now is we x is the array that we have already fattened the image. Yeah, so now the image is basically in the 12288 times 209. Yeah, so if you remember we have total have 209 images. Yeah, so this m is 209. Yeah, and this is the layer dimension. Yeah, so nx, nh, and ny. Yeah. So, okay, now this is the place that you have to code yourself. Yeah. So basically, now we have to, this none is basically is a function. It's just a one line of function, one line of code that will initialize the parameters. Yeah. So this function you will be using like one of the function here. Yeah. So yeah. So you can choose like which function is suitable for here. Yeah. So you can like initialize the parameter by using that function. Yeah. So the input so what is the input of the function? I have already tell you. Yeah. So basically it's maybe like this or DA or this one. Yeah. So it's basically a simple function. Yeah. So you can just replace the non with your function. Yeah. If I'm not mistaken, I haven't run this. Yeah. So I've run this first. Okay. Yeah. So I'll give you like 1 minute, yeah, to complete this one. Yeah. And then I will answer some of the question. Yeah. Can you show us the NH higher or lower than 7? You can like just you can like see into me. Okay. Yeah. So yeah. So if you have any question, yeah, you can ask inside the chat, and then we will like yeah, and then we will like have the helper. Yeah. So you will like be assigned into the breakout room. Yeah. So the helper will like help you. Yeah. Yeah. So okay. So yeah. So let's do this. Yeah. So parameters. Yeah. So we are because parameter we want to initialize all our weight and bias, right? Yeah. So we will be using this function initialize parameters. Yeah. So the input will be nx, nh, and ny. Yeah. So you can just copy inside. Yeah. So here, right? Yeah. Initialize parameters. Yeah. So it will be autofill. Yeah. So you see the arguments is here already. Yeah. You can nx. Yeah. N H and Y. Yeah. So okay. So after we obtain the parameters, right? Yeah. So this is basically a dictionary that store your W1, B1, W2, and B2. Yeah. So now we try to extracting the parameters from the dictionary. Yeah. So this W1, B1, W2, B2 is the key of the dictionary. Yeah. So like if you are not familiar with dictionary, you can go for our Python workshop recording. Yeah. So yeah. So the parameters will get the weight and biases out of the parameters. Yeah. So that we can obtain the W1, B1, W2, and B2. Yeah. So after that, we'll like loop and then we will like fit our input inside the model. Yeah. So okay, after we obtain the initial value of the weight and biases, right? Yeah. So that means our whole model is ready already. Yeah. So now we can input our 1D array of the image. Yeah, inside the model. Yeah. So now we want to this line of code is basically is we run the 1D array from the first layer, the input layer into the hidden layer. Yeah. So the A1 is the output of the hidden layer. Yeah, and then cache is basically is the output and also the weight of the in this in this process. Yeah. So this basically we are using like two same function for this one. Yeah. So basically you can like remove the none and then you can like replace it by one of the function up there. Yeah. And then the input will be x w1, b1, w2, and b2. Yeah. So this input will be is not the input inside the whole function, but the input in the two function altogether. Yeah. And the output will be A1 is basically is the output of the hidden layer, right? Yeah, and then we use the output of the hidden layer, and then we feed it into the last layer, the output layer, and then we will get the A2. Yeah, so A2 is basically the output of the whole model. Yeah. So you have like 2 minutes to complete this two none. Yeah, so you can like remove it and then you like replace it with a function up there. Yeah, basically these two are the same function. Yeah, just the input is different. Yeah, so you can like consider like which function you is suitable for here. Yeah. Yeah, so I explain again. Yeah, so for this function, basically we have to feed our input inside the input layer, and then we want to obtain the output in the hidden layer, which is A1. Yeah, so this one we have to feed our output of the hidden layer, and then we will obtain the output in the output layer, which is A2. Yeah. So okay, so if you are like not familiar with function, right? Yeah, so basically function, these three parameters is basically what is the input of the function. Yeah, so if you like plug in more things, right, it will maybe it will give us some error, or you plug in the, because the parameters is a dictionary, right? Yeah, so if you like maybe you plug in a list or a string, you will also have some error. Yeah, so the like the type of the type of the variable and the number of variable plug you fit inside, right, is also important. Yeah, so okay, time's up. Yeah, so in order to obtain our first, the output of the hidden layer, right? Yeah, so we have to use the function called, yeah, sorry. Yeah, linear activation forward. Yeah, so the input is the A previous, the weight, the biases, and the activation function. Yeah, so yeah, so we can use the linear activation forward. Yeah, so you can see the A previous, WB, and activation function, right? Yeah, so what is A previous? Yeah, so what is the input to the, where is the input to the hidden layer? Yeah, it's basically is the input to the first layer is the input of the input layer, right? Yeah, so this is basically is X, because X is the input to the input layer. Yeah, and then we want it to multiply by the weight, right? Yeah, by W. Yeah, so but we want only want the weight connected between the input layer and the first hidden layer. Yeah, so the W is only W1. Yeah, so the B is also B1, because we only want the weight and the biases that connect, and bias that connect between the input layer and the hidden layer. Yeah, and the what is the, because we want to obtain the like output of the hidden layer. Yeah, so but uh as I say in the PowerPoint, right? Yeah, so before the output, right, the input we have to go through some activation function. Yeah, so now we are using the ReLU function, right? Yeah, so the activation function you can by using the sigmoid or ReLU. Yeah, so now we are using ReLU in our this in this function. Yeah, so Okay, so now we obtain the A1, which is the output of the hidden layer. Yeah, so now we want to feed the A1 inside the output layer. Yeah, so this is also linear activation forward. Yeah, so previously the X is the input to the model, which is the X. Yeah, so now the input to the output layer is the output. The input to the output layer is basically the output of the previous layer. Yeah, so it's basically A1. Yeah, and then we want the weight that connected to uh the weight that connected to the previous layer and the output layer. Yeah, so this is W2 and this is B2. Yeah, and the activation function we use is sigmoid. Yeah, so we type sigmoid here. So if you are like interested in what is the code inside the function, yeah, so you can try to like go to see the Python file. Yeah, so okay. Yeah, then we will so like uh A2 is the basically the output of the whole model. And then the cache 2 is the like the intermediate output and also the weight and biases, because we don't want it to like disappear, so we store it inside the cache 2. Yeah, so okay, after we obtain the output of the model, right, we have to compute the cost or loss between the output and the actual label. Yeah, so is if the like actual label is 1, yes, but the output is 0.1. Yeah, so there are like a lot of difference. Yeah, so the cost of course will be a very large. Yeah, so this compute cost, you basically you can replace this none with a function that can compute the cost. Yeah, so we have 1 minute with this. Yeah, so for our previous workshop or this workshop, like all the materials will be like uploaded in the our MLDA YouTube channel. Yeah. So but this takes some time. Yeah, because we have to like process the video first. Yeah, before we like put it there. Yeah. So okay. So how the function to compute the cost is basically this compute cost. Okay. Yeah. So we will be using compute cost. Okay. Yeah. So the input will be the AL. The input will be the AL. AL is the like the output of the model. So this is A2 and Y is the actual label. Yeah. So yeah, as mentioned as the compute cost here. Yeah. So okay. So after we have the loss already, the cost or the loss already. Yeah. So we have to compute the gradient with respect to the weight. Yeah. So now we initializing the backward propagation. Yeah. So we obtain the di2 by this function. Yeah. So if you want to know like why this function, you can try to like this is a function to like calculate the gradient by using numpy. Yeah. So yeah, and then we will start our backward propagation. Yeah, now we have our DA2 already. Yeah, so now we are want to compute our DA1, DW2, and DB2. Yeah, it's basically is the loss function, the partial derivative of the loss function as with respect to the weight and biases. Yeah, so because there is a very complex formula, yeah, so we have already like replaced this with a helper function. Yeah, so this none will also be one of the function up there. Yeah, so you can replace the two none with the same function. Yeah, so yeah, Yeah, so let's do this. Yeah, so now we have like to compute the gradient, right? Yeah, so we are using the function linear activation backward. Yeah, so the input is the like the gradient of the like on the layer more backward, and then the cache and the activation function. Yeah, so this will be linear activation backward. Yes, this autofill. Yeah, so the input will be dA. Yeah, so what is dA? So because now we are in the output layer. Yeah, so we want to obtain the gradient at the hidden layer. Yeah, so the input will be from the back. Yeah, so this is dA2, and this is cache 2. Yeah, because we only want the weight and biases between the store previously. Yeah, the connect between the hidden layer and the output layer, right? Yeah, and activation function, because we are like propagate from the back, right? Yeah, so we are using sigmoid. That is the activation function of the last layer. Yeah, this one. Okay, so after this function, right, we obtain our dA1, dW2, and dB2. Yeah, so here we will also like use the linear activation backward. Yeah, so the input, because now we want to obtain the gradient at the input layer. Yeah, so now we are in the hidden layer. So, yeah, so we want to like obtain the output, the gradient in the input layer. Yeah, so this input will be dA1. Sorry, yeah, and now we want to like use back the gradient and biases that we the weight and the biases that we stored previously. Yeah, so we will be using cache 1. Sorry, yeah, cache 1, and the activation function of the like hidden layer. Yeah, so this is relu. Yeah, so after this function we can obtain the dA0, dW1, and dB1. Yeah, so like after this, right, we only want the dW and dB. Yeah, so just now we already like initialize the grad is the empty dictionary. Yeah, so now we are storing this dW1, dB1, dW2, dB2 inside the dictionary with the key as the same name as the dW1, dB1, dW2, and dB2. Yeah, so like after we obtain the gradient, right, we have to update the parameters. Yeah, so this will also be a function up there. Yeah, so as you can see, yeah, so this is the last function that we are going to use, which is the update parameters. Yeah, so in order to obtain the whole to update the whole parameters, right? Of course, we have to input the so we have to input the parameters that is uh, we have to input the parameters that we obtain here. Yeah, so so we update the parameters, and then the input is the old parameters. Yeah, sorry, this is parameters, and then this is grads. Yeah, so the dictionary that contain the dW1, dB1, dW2, and dB2, and then the learning rate. Yeah, so learning rate. Yeah, so this learning rate is already obtained. We already define here. Yeah, so you just obtain the learning rate. Yeah. Okay, and this function can update our parameters. Yeah, so parameters is also a dictionary that store our new W1, B1, W2, B2. Yeah, so we will extract the new W1, B1, W2, B2 from the parameters. Yeah. So this is basically print the cost after 100 iteration. And then this will plot the function after the end of the training. And then it will return us a dictionary of the parameters. Yeah, so, okay, so okay, if we do until here, right? Yeah, so we obtain our new W1, B1, W2, B2. Yeah, if our iteration is not ended yet, yeah, we are still we will still want to loop again. Yeah, so we will use the new W1, B1, W2, B2, and because the X is not changed, right? The input is not changed. Yeah, so we will put it here again. Yeah, so we will calculate the output of the X and the weight one and bias one, and then we obtain the A1. And then we calculate the A2, and then we compute the cost, and then we compute the gradient. Yeah, and then we will update the parameters. Yeah, so this is a loop. Yeah, basically we want it to loop maybe like 2000 times. Yeah, so that we can update our parameters. Yeah, so that our like accuracy will increase or our loss will decrease. Yeah, so let's run this. Yeah, remember to run all of the cell previously. So here we can see that now we are calling the function. Yeah, so that we can see like how our cost how is our like cost be like. Yeah, so yeah, no problem here. Yeah, so okay, initially we have the cost of 0.69. Yeah, there is a very huge cost. Yeah, then we can see like every 100 iteration, right, our cost start to decrease. That means that we are having a weight and biases that can help us to reduce have a higher accuracy, so that our cost will decrease. Yeah, so it's basically our weight and biases is improving every iteration. Yeah, so we are looping it at the number of iteration of 2500 iteration. Yeah. So yeah, so if you have if you have a problem with your code that you cannot run, yeah, so later after this workshop, I will be sending the answer, the whole Google Drive that have the answer of the notebook and the PowerPoint to you all. Okay, yeah, so we can see the loss is decreasing from the beginning to a very low value. Yeah, so this is the this considered as a good decreasing. Yeah, so okay, now this function basically will sorry, yeah, so this will predict the will calculate the accuracy inside the inside the train set. Yeah, this is we cannot consider is the output is good because we don't predict it by using the test set, right? Yeah, so the train set is pretty good. Yeah, 0.00 by 999%. Yeah, so okay, so after this, now we are doing a L layer neural network. Yeah, so now we are doing the neural network with the dimension. Yeah, so 1, 2, 2, 8, 8, 20, 7, 5, and 1. Yeah, so we have the input neuron of 1, 2, 2, 8, 8. Basically, is 3 times 64 times 64 of the pixel value. Yeah, so and 20 for the first hidden layer, 7 for the second hidden layer, and 5 for the third hidden layer. And then we have 1 neuron for the output layer. So this is a 4-layer model. Yeah, so because the implementing this model is quite complex. Yeah, so we will already like do some function to help you all. Yeah, so basically we have 4 layers, right? Yeah, 3 layer is the hidden layer and the final layer is the output layer. Yeah, so the 3 layer will be L minus 1 is 3, right? Yeah, will be ReLU function. And then the output layer will be a sigmoid function. Yeah, so this initialized parameters deep will be initialize all the weight inside the, yeah, we will initialize all the weight inside the model and the bias also. Yeah, and then we'll return the parameters. Yeah. So the dictionary containing your parameters W1, B1 to WL, BL. Okay. And then this L forward is want to obtain the output and the cache from the next layer. Yeah. So if this is the input layer, we want to obtain the output of the first hidden layer. Yeah. So it accept the X is the input and then the parameters. Yeah. Parameters is this one is the whole parameters of your model. Yeah. And we will compute the cost. Yeah. So basically this will compute the loss between the output of the model and the actual label of the image. Yeah. And then we will compute the gradient by using the L model backward. Yeah. So you are like we will input, the input is the output in the final layer, right? Yeah. And then Y is the actual label and then the caches. Yeah. So now the caches is basically a dictionary that store all the weight and biases. Yeah, but not just in between layers, but all the yeah, is containing every cache of linear activation forward. Yeah. So the output will be a grad, a dictionary with the gradient, DA, and then the updated. Yeah. So and we update the parameters. Yeah. So the input will be the parameters. Yeah. So parameters of all your weight and biases, and then the gradient of all the dB and dW, and then the learning rate. Yeah, so the layer dimension is here. Yeah, so since we are running out of time, yeah, so actually this is basically the same as the as the like the function. Yeah, so this will be a L layer model. So input is X and then the label Y and then the layer dimension. Yeah, so the dimension and the new dimension, the layer and the number of neuron and then the learning rate. Yeah, so the number of iteration and then print cost. Yeah, so if you print cost every 100 iteration, if this is set to true, then okay, parameters, right? Yeah, so we will be initialize parameters deep. Yeah, so we will be using this function. Yeah, so we initialize all the weight and biases inside the model. Yeah, so yeah, so you can see this just the input just layers dim. Okay. Yeah, the layer dim is this one. Yeah, so okay, then we obtain the parameters, which is the W and B. Yeah, so and then we loop and then we will. Okay, so basically this we want to do the forward propagation. Yeah, and then we are using L model forward. Yeah, so this L model forward will automatically loop through all of the intermediate hidden layer. Yeah, you don't need to like call this function again and again. Yeah, you will like loop through all of the intermediate layers. Yeah, and then we can directly obtain the output from this function. Yeah, so this is L model forward. Yeah, so the input is X is the 1D array of the image, and then the parameters. Okay. Okay. So the AL is the output of the whole model. Yeah. So this function will propagate through all the intermediate like neurons or layers, yeah, and then we can directly obtain the AL, the output, and the caches, yeah, the dictionary that contain all the cache in between the layer. Yeah, so the cost and then is still the same. Yeah, so we will compute the cost with AL and Y. AL is the output of the model. Y is the actual label of the image. Yeah, so after we obtain the cost, right? Yeah, so we'll try to do the backward propagation. Yeah, so this here we are using the L model backward. Yeah, so this model you input the AL. Yeah, so it will like calculate all the A, D, W, and DB in for all the intermediate layer. Yeah. So if you are like interested in what happened inside the function, yeah, you can go and take a look at the Python file. Yeah, so this is L model backwards. So the input is AL and Y and the caches. Yeah. So okay, after that we'll obtain the grades dictionary that contain the DW and DB. Yeah. So that after that we want to update the all the weight and biases. Yeah. So this is the update parameters. Yeah. So update parameters. Yeah. So the input is parameters. The all parameters. This one is, and then the grades and the learning rate. Yeah. So basically, just now in the PowerPoint, I have said that basically how you update is the O parameter, O weight, and then we subtract by the learning rate multiplied by the gradient. Yeah. So basically, this is the whole function, and this will print the cost every 100 iteration, and then this will plot the cost, and then we will return the parameters. Yeah. I'm so sorry that we are running out of time. Yeah. So that we will like go through faster. Yeah, so basically this is all you need to do inside the coding session. Yeah, so like so after that they will be just showing the output. Yeah, so we run this. Yeah, so we're waiting for the iteration. Yeah, so we can see that initially the cost is 0.69. Yeah, so and then the after iteration, yeah, so we can see the cost is decreasing. Yeah, so yeah, so like after this workshop, so the answer of this notebook and the PowerPoint and the Python file will email to you all. Yeah, the Google Drive will email to you all. Yeah, so don't worry if you miss out something. Yeah. Why don't we have to declare n, h, n, x, and ny? Yeah, actually we declare already, right? Yeah, this layer dimension is basically nx is here. So this three is the nh and one is the ny. Yeah. So, but for to make you to be simple, yeah. So we are combining all of them inside the layer dims. Yeah. So layer dimensions. Yeah. So we can see the frame rate is decreasing. Yeah. So we can predict it by using the train set. Yeah. So you can see the is 0.09998. Yeah. So this is for the train set. Yeah. But maybe the model have like memorized the features or the images and the label. Yeah, so the train set is quite good. Yeah, so what about test set? Yeah, sorry, on the test set, it just 0.74. Yeah, so maybe this is like not so good. Yeah, because this is just a simple layer. Yeah, maybe the output is not so good. Yeah, so this function will print out all the mislabeled image. Yeah, you can see. Okay, so this is prediction is cat. Yeah, so the class is non-cat. Tabulation is non-cat, but the class is cat. Yeah, so this is the mislabeled image inside the test set. Yeah, there are quite a lot. Yeah, that means they show that this model is not doing well. Yeah, it just have the accuracy of 74%. Yeah, okay, now we will be testing by using our own image. Yeah, so okay, so okay, you found over here. Yeah, so the neural network workshop. Yeah, so have a folder called images. Yeah, so there are 3 images here. Yeah, my image, rabbit and Tesla cat. Yeah, so we try to now we try to verify our model by using the image Tesla cat. Okay, so my image is this image, and then my label y is 1. So this is the true class of your image. So 1 is cat, 0 is not cat, right? Yeah, so Tesla cat is cat. Yeah, so the label is 1. Yeah, so this will basically flatten the image, and then you resize the image into the shape of 64 times 64. And then divide it by 2.5, and then it will predict the image. Yeah, so let's see. Oh, sorry. Yeah, Tesla cat. Oh, sorry. This is Tesla dash cat. Yeah, so run this. Yeah, so accuracy is 0. Yeah, your L layer model predict a non-cat picture. Yeah, so that means our model is not functioning well. Yeah, so that our model is like predict a non-cat picture. What's then? Why not we change the maybe to rabbit? Rabbit, right? Yeah. So my label y is 0 because this is the actual label of the image. Yeah. So this is 0. So let's run this. Yeah. So accuracy is 1. The y is 1. Your model predict a non-cat picture. Yeah. So this is non-cat. And then the uh, output is non-cat. Yeah. So the accuracy is 1. Yeah. So what about my image? Yeah, my image. Yeah, my image. Yeah, but because we don't know what is the label, what is the actual label. Yeah, so just leave it. Yeah, just run. Accuracy is 0. The y is 1. Your L model predict it as a cat picture. Yeah, so this is cat picture, right? The output is 1. But our label is 0. Yeah, so of course the accuracy is 0. Yeah, so we change the actual label to 1. Then we run again. Yeah, so this will be, yeah, so this will be, your accuracy is 1. Yeah, so your y is 1. Your L layer model predicts a cat picture. Yeah, I'm sorry that I run out of time. Yeah, so the all of the notebook, the code, and the PowerPoint will be shared to you like after this, like quite like maybe like 1 or 2 hours after this workshop. Yeah, so um yeah, so um what does flattening the image do? Yeah, so because our model is just we are defining a 1D neuron. Yeah, so of course we have to we want the like image to be in a 1D shape, but not 2D. Yeah, yeah, you can like if you see the image it for like one in a like just you can see the image. Yeah, so it's basically is a 2D image, but you see in the pixel value it will be a 3 layer times 2D. Yeah, so it will be a 3D image. Yeah, so yeah, so I hope everyone learned something from this workshop, and please help me to like yeah, so um yeah, so this is appendix. Yeah, so like yeah, so you can see it later. Yeah, so please help me to fill in the feedback form. Yeah, sorry. Yeah, so I will be also pasting the feedback inside the chat. Yeah, so this is Okay. Sorry. Yeah, so this is the feedback link. Yeah. Yeah, so please help me to fill the feedback form so that we can improve next time. Yeah. Yeah. Yeah, so yeah, I'm back. Yeah, so that's yeah, so later on, like after the recording of this Zoom is come out, yeah, so I will like share the recording and also the Google Drive that consists of all of the like the answer to the notebook and also the PowerPoint and also the Python code. Yeah, so I think my colleague shared a wrong link. Yeah, so later maybe like after the Zoom recording is come out. Yeah, so